Yes, sir, you can start now.
All right. Okay. Good afternoon. We have covered some part of the high pressure physics so far. What we are going to cover in next 6 lectures is going to be quite a deviation from what we were talking so far. The field is mostly called dynamic compression, also called shockwave physics. And we will see there are some fundamental differences between what we studied, discussed so far, and what this field has in store. In the lectures so far, what we noticed is that time was not a factor, except when one was talking about kinetics or phenomena, something like phase transitions and so on. Then one invoked time as to how the daughter phase emerges from the parent phase as a function of time. However, for the application of pressure, time was not an issue. Also, the temperature could be changed independently of the pressure. One could do experiments at high temperature, high pressures, or one could do experiments low temperature, high pressures. So these two parameters could be varied independently. And the microscopic strain that was discussed so far was either hydrostatic or quasi-hydrostatic, except in the last few lectures when Dr. Pandey invoked in the consequences of plastic deformations in the solids, specifically how the plastic deformation affects the phase transitions. So far, therefore, we discussed studies about the physics of the studies of materials under a variety of high pressure and thermal conditions. You mentioned it could be combinations of both high temperature, high pressure, etc., etc. And a very large number of techniques could be employed to investigate the phenomena under the pressure. I mean, whether they were spectroscopic techniques or X-ray diffraction or X-ray based techniques or synchrotron based techniques. There were a variety of those techniques. We did not discuss one aspect which could have also been covered using diamond anvil cell technique that borders on what we are going to cover hereafter and what was covered so far. I think it was out of an oversight. These are called dynamic diamond anvil cell studies, into which the pressure around a chosen value can be changed very rapidly. And then one can study what happens. There are, in fact, dedicated dynamic diamond cells now at some of the synchrotrons where people are investigating studies of, for example, unstable structures when you quickly change the pressure around a certain value. So if the time permits, probably one of us will cover that. Otherwise, one can look into the literature or survey through the website under dynamic diamond anvil cell studies, and you will see there are quite a few of very interesting studies which come in that category. So most of the experiments, except the ones which were done at synchrotron, could be done in the laboratory, say Raman or IR, or variety of other studies that could be done in a small lab. In summary, what we did in terms of pressure is described here. This is that red line. The pressure was raised in a cell and it could be kept on for as long as you wanted. You could finish various studies. In fact, one did one can do X-ray diffraction and then come on and do Raman scattering and do some other studies while the pressure is locked at that value. The other extreme is that up to a certain value of time, there is zero pressure, and suddenly the pressure gets switched on abruptly, and then the material is under some pressure. Obviously, this cannot be very long because this kind of a phenomenon, as we will talk about, can last only for a certain amount of time. Eventually, this steady state will fall off, the pressure will fall off. So we have a small window of time into in which one can make the studies. In between of these two limits is one can raise the pressure smoothly to a particular value. These are called ramp compression. So we have under high pressure static compression investigations of materials. The other extreme is shock compression of materials. And in between is a ramp compression of materials. In terms of thermodynamics, the static pressure studies are called isothermal studies, in which the temperature is not changed as a function of time. So we can freeze the temperature at a particular value and make measurements. The other extreme is shock, where we suddenly raise the pressure. The moment we suddenly raise the pressure, temperature also is intertwined and the temperature also changes. And therefore, one simultaneously gets a package or states of a given pressure and temperature. We will see how one describes those states, but that comes as a deal. I mean, you can't separate these two things, these two thermodynamic variables. Ramp compression is in between. In fact, you can tweak this rise time in a systematic manner so that the temperature increase could be kept very small. So depending on the rise time, one can get the states at one limit being almost close to static and the other almost going to the shock compressed state. The field of the shock wave or the physics of it, in fact, has its roots in a lot of defense applications. But before we talk about it, let me give some key references. The first book by Zeldovich and Reza is a well-known treatise on shockwave physics, and it mostly deals with the hydrodynamic phenomena of shock compression, widely referred to. So those of you who are interested in going deeper into the subject may look into this. Then there are from time to time other books which got published. For example, one is High Pressure Shock Compression of Solids, edited by Jim Assay and Shahinpur. It also has, incidentally, an article by Dr. Sikka, Dr. Godwal, and Dr. Chidambaram, which was contributed from BARC, summarizing the investigations on equation of state under static as well as dynamic pressures done at Trombay. Then reference 3 is a primer on the shock wave compression of condensed matter by Jerry Forbes. One can go through a variety of details related to the condensed matter physics and shock compression. There is a very popular book by Glass, Shock Waves and Man, interesting reading for those of you who don't want to develop deep expertise into the subject, but still would like to know things which a common man should know about the shockwave physics. And there is a well-known review article by George Duval and Graham, Interviews of Modern Physics. There are various people who have given lectures on this subject from time to time, and one can search web to find out, depending on the topic that you want to see, there'll be some lectures. I have personally interacted with Professor Yogi Gupta at Washington State University and had access to his lecture notes. Some of the things which I am going to talk about, I would borrow from some of the things which he covered in his lectures uh, in US. The shockwave physics as a subfield of high pressure physics actually started somewhere in 40s. In fact, in 1947, American Physical Society meeting uh, had about 21 papers on shockwave physics. First time it appeared in American Physical Society, 21 papers. And it also had a theoretical paper by Hans Bethe, who was known as a pioneer in this field, as later work proved. In fact, somewhere prior to that, I think in 1942, he had written a report on theory of shock waves for an arbitrary equation of state. It was a restricted report, not available to many people, but that is kind of the first published report that one can refer to. Based on some of the work of the shockwave physics, um, there were inputs into what one calls as the first nuclear fission device, which was tested in 1945. So the field of high pressure physics have in some ways been viewed as related very closely to the defense work or nuclear work. In fact, the first general physics interest in the subject uh, was raised by a publication in Journal of Applied Physics in 1956 by Bancroft and Cleves, who studied phase transformations in iron under shock compression. And they claimed that iron underwent a phase transition with a large volume change at 13 GPa. It immediately ran into controversy because the static pressure work of Bridgman had claimed that the phase transformation somewhere in tens of GPAs is very sluggish phase transition and doesn't happen at 13 GPA, it happens at higher pressures. However, the people in the shockwave physics, the people who were doing shockwave experiments, were convinced that it has something to do with the phase transformation. And probably what is being viewed as extremely slow phase transformation under static pressure has become very fast phase transformation under shock compression at 13 GPa. And the root cause for that was speculated at that time. That could be the shear, the presence of the shear stresses, which are unavoidable or naturally arise in shock experiments, as we'll see as we go along. So Bridgman revisited his experiments and found out that his static pressure scale was wrong. I did find that the transformation does indeed take place at about 13 GPa. However, it takes several days before the transformation is completed, and therefore ruled out that what the shock people observed at 13 GPa was the same phase transformation. However, his later experiments in which he introduced shear showed the transformation indeed can happen very fast and at 13 GPa. So that is the first time with this controversy about the phase transformation iron, which brought the shockwave physics into the mainstream of physics. And a lot of work since then has been done. It's a It's widely covered in every 2-year meeting which takes place in the subject called tropical meeting on the Shockwave Physics under American Physical Society. Actually, the development of careful experiments took still a lot more time, maybe another decade, how to design well-controlled experiments, reproducible experiments. And I think it's somewhere in 50s that first carefully carried out experiments were published. From the perspective of physics, shockwaves help achieve far more extreme thermodynamic states of matter than the static pressure can help. The pressures or the thermodynamic conditions which one can reach with the help of shock waves could be representative of Earth, exoplanets, even stars for that matter. We'll see shortly the kind of conditions that one can reach under shock compression. One can, with the help of the insights gained by shockwave physics knowledge, can interpret what happens when the meteor or asteroids impact the planet. All these basically states which from one end to should I say crust of Earth to the states of matter in stars could be reached because the shock state, as I mentioned, has pressure and temperature rise simultaneously. So that these two, temperature and pressure rise, are intertwined. And so one can, when goes to very, very high level of shock compression, these two simultaneously rise. Real-time measurements can also help study the physical and chemical changes in a wide variety of materials. There is another field or a subfield of shockwave physics which we are not going to talk about. It is called detonation physics. Particularly if one is dealing with the materials which are chemically reactive, when you subject them to shock conditions, they also interact and release energy, and as a consequence, the shock wave amplitude can grow. That's a field in its own right. So in all our discussions in this topic, we will not talk about materials which are energetic. We will rather talk about materials which are inert, therefore do not contribute to the energy generation and increase in the shock wave amplitude. The real-time experiments which can be done with the shock wave compression are in fact have very severe constraint compared to the static pressure experiments. One has to finish these experiments at upper limit of a few microseconds, and more likely these days in a few nanoseconds. So we have a very small window in which the experiments have to be carried out. Also, in addition, unlike the static pressure experiments, shock wave experiments are invariably destructive. We do one experiment, we're done. That entire material and assembly is gone. And when we redo another measurement, one has to reassemble everything, scratch. And as we'll see, that what actually makes this an expensive field of research too. So also because it's as I mentioned, it helps reach thermodynamic states from one end to the very low pressure and temperatures to extremely high pressure and temperatures. One can very easily visualize that this field has necessitates its understanding requires knowledge of applied mathematics, classical physics, chemical, quantum physics, material science, and even astrophysical situations, something like the position of state of stars and so on. Before we launch into more serious aspects of shockwave physics, let us recapitulate on some of the things that we discussed. I think Dr. Pandey covered this. So on, you see this is a relationship he talked about, that if you apply stress on a material, it gives rise to strain, and the coupling is stiffness matrix. You imagine that you apply only one direction, stress in only one direction, that is sigma 1. Rest all stresses are 0. Because the stiffness constants are not 0, at least even for cubic, some of them are non-zero. I'll show you in a minute. Then you can very quickly see, even if this is non-vanishing, at least these three strains will be non-vanishing. So uniaxial stress does not mean uniaxial strain. Likewise, if one had only one component of the strain, say epsilon xx or epsilon 1, then again you would have several stresses which will get generated in this. Trying to do the matrix multiplication, you quickly figure it out that a uniaxial strain situation is not a uniaxial stress condition. What we see is that, for example, compliance constants for a cubic material, we have certain non-vanishing of diagonal components, and therefore, even for a material as symmetrical as cubic, you would have a uniaxial stress giving rise to non-uniaxial strains and vice versa. Why do I say this? Here is a summary of this. Under the hydrostatic pressure conditions that we mentioned in our earlier talks, we implied that if we had an object, there is an equal amount of pressure which is being applied from all sides. Like, for example, something immersed in a liquid, that you apply pressure in a liquid, and something which is in the center will feel equal amount of pressure on all the sides. So hydrostatic pressure. More often than not, hydrostatic pressure would give rise to hydrostatic compression in cubic or high symmetry materials, but not necessarily in all materials. For example, in hexagonal materials, even if you have hydrostatic pressure, the strain or compression need not be hydrostatic, it could be anisotropic. Other condition is that you apply uniaxial stress. You had dotted as the initial shape. As you apply a stress, then you see this gets compressed here, but these two sides expand. So this gives rise to a strain this side as well as strains in this side. This is what I meant. A uniaxial stress, it doesn't mean uniaxial strain. Shock experiments, as we'll shortly see, are actually uniaxial strain experiments. We compress a material in terms of strain only in one direction. So this becomes this. I mean, a cube, let us say, becomes a tetragonal kind of, or a cuboid kind of a situation. But then one has to view this as a situation into which you have a stress longitudinal, which is along the direction you applied, and also lateral. So when we therefore talk about shockwave experiments, though the strain is uniaxial, stresses are not. Uniaxial strain that one achieves in shock experiments, as you will see shortly, is achieved by inertial confinement. And it's important to understand shock compression is not just a volume compression. A lot of things happen under shock compression. Defects get generated, a variety of defects get generated. Plastic deformation happens, shear stresses there, all kinds of things happen. So the material subjected to shock compression, in addition to temperature and pressure, also has a lot of underlying things which are happening. And one has to therefore, to understand the entire physics of what happens at the shock, one has to double into several subfields. As we go along, we will restrict our discussion to one-dimensional shock waves. Obviously, in nature as well as in applications, not all shock waves are one-dimensional. In fact, many of the applications necessarily require it to be non-one-dimensional. But for simplicity of understanding, what we will do is we will restrict this to the one-dimensional. Here is what I meant in one-dimensional. When you think of situation is infinite in, let us say, y and z direction, and only certain dimensions along. We call this as x direction. So we apply, let us say, compression, or should I say, uniaxial compression, or we make an impact on this surface. So this material will get compressed in this direction. Let us focus on this small cube here. So this will get compressed here. If this had infinite dimensions on y and z, then it will be truly uniaxial because no information from the edges will ever reach state. So one can actually see a state which is truly uniaxial, and as I said, is generated by the fact that it is inertially confined. These surroundings just don't move. The shock and the ramp compression, therefore, represents uniaxial strain. Okay. Consequent increase in energy has two components. One is the mechanical, which is the compression part, which we mentioned this, and also dissipation, which is the temperature part. Macroscopically, this state is homogeneous. Okay. However, microscopically, there could be certain issues, and if time permits, we'll talk about it. But macroscopically, this compression is homogeneous, irrespective of the nature of bonding. So whether you are compressing the liquid or you're compressing diamond as hard material as diamond, this state is really homogeneous. The state has compression, it has deformation, and temperature rise, all taking place in short time. And it is not possible to disentangle these features. Critical treatments almost invariably assume that it is in the state is in thermal equilibrium. Though we invoke a rapid increase in pressure across the shock front, we necessarily assume that it is in thermal equilibrium. We will talk about, if again time permits, that there are situations where thermal equilibrium will be violated, but for most of the investigations, it is reasonable to treat as in thermodynamic equilibrium. The state is in thermodynamic equilibrium. And that means that we should not treat electrons having a different temperatures and cores or atoms having different temperatures. So they are in equilibrium. They basically, the treatment can be done in the Born-Oppenheimer approximation. That is, the electrons move very fast and adjust themselves to the configurations which the atoms take. Shock generation can be done by a variety of ways. Chemical is detonation, as we'll say, using explosives. Most of the early work heavily depended on this. Explosives were used in a very careful geometries to generate shock waves. Then several impact facilities were generated, which could subject the materials to as high a pressure as 10 megabar. High intensity lasers now these days are widely used to subject materials to very high shock pressures, up to 800 megabars, and pulsed power sources, something like a Z machine and so on, can also go to very high pressures. In fact, other limit is the nuclear explosions. Actually, this number is more appropriate for nuclear explosions. It can subject the materials to almost 4,000 megabar and so on. So you can see that at that kind of pressure, electrons are ripped off atoms. So you may say the nuclei are floating in the sea of electrons. So that's the other extreme of what can happen to matter under shock compression. Here are a few photographs of typical is how the shock wave is generated in the laboratory. This is called gas gun. And it has actually, this is a two-stage gas gun. It has one stage into which a projectile or some object which flies is subjected to with the help of, let us say, some explosive, and it flies in, and then somewhere here, it compresses the gas in between to extreme high value, which ruptures, and then flies the final projectile into this and makes an impact on the object which you want to investigate. So this is called gas gun. As I mentioned, that using this, one can achieve pressures of the order of 10 megabar. Lasers, here is an extreme example of lasers being used to carry out shockwave experiments. It's the National Ignition Facility in Lawrence Livermore Lab in US, where 192 wavelengths are synchronously and in parallel pumped, and they're allowed to fall on the object so as to generate terawatts of X-rays and huge amount of compression, shock compression. The third one is Z machine, and in which something like capacitor banks having a large voltage or suddenly discharged, high currents flow, a large magnetic field is generated, which is then coupled on to mechanically to pliers and so on to generate extremely high pressures to study shockwave physics or shockwave compression of materials. We will discuss, as I mentioned earlier, essentially one-dimensional waves. As I said, in principle, in situations, actual situations require more than one-dimensional waves. In fact, even spherical and cylindrical waves are also one-dimensional because in spherical it is essentially radial, and in the cylindrical also it is therefore as a function of radius. However, it has an additional complication that the amplitude or the strength of the shock wave varies as a function of the radial distance. If it is a converging wave, either in cylinder or in a sphere, that will amplitude or the intensity of the shock wave will increase manifold as it gets converged towards the center. So a huge amount of non-linearities would emerge, and that becomes a very complicated field. And we will not talk about it in the rest of our sessions. This had we will restrict ourselves to one-dimensional planar waves. That is, all variables will be only function of one direction of propagation of wave. X and Y and Z will not be relevant. Most waves in physics are, is discussed in terms of linear waves, and this is a well-known people have used it as a electromagnetic waves and sound waves and so on. And solution of this is that phi as a function of x minus ct or x plus ct, depending on whether it is moving in the positive or a negative direction. So phi is the amplitude of disturbance. It could be electromagnetic or it could be mechanical. And c is the speed of the disturbance. And for mechanical waves, a medium is necessary. It can happen only in a medium. For a material, it would represent elastic waves, whether it's longitudinal or transverse. And in that case, c will be the speed of the sound, which depends on the density. So obviously, the speed of the sound is less in gases and much larger in solids. Now let's define formally what a shock wave is. A shock wave is represented here. For example, I mentioned earlier, sharp discontinuity between a state, initial state, which we define as rho naught in density, P naught pressure, and rho naught. That is take that it is a zero pressure to start with, and equilibrium density, ambient condition density, and it isn't moving object, so it is at rest. Then this sharp discontinuity, when it lasts into this, if it is large enough that it gains the speed of its movement, becomes supersonic, we would call this as a shock wave. So that is a necessary definition of a wave to be shock. A shock wave is therefore a large amplitude disturbance propagating at supersonic speeds, across which several thermodynamic variables such as pressure, density, internal energy, they change in almost discontinuous manner. So the key factor in shock is that it has to be supersonic. Anything which is subsonic or moving with the speed of sound does not qualify itself to be a shock wave. We know that in nature there is never a perfect discontinuity. Okay? That's back the same when a shock wave is launched into materials, and it does happen that it gains certain finite width, which is basically because of thermal conduction that will take place across this interface, or viscosity. There will be kind of faults generated suddenly when this mechanical state changes. Large amount of faults are generated, dislocation, so on. All that's introduced a drag on this, and so one can introduce something like artificial viscosity, gives certain finite dimensions to this. In fact, in early theoretical work, this aspect of viscosity was artificially introduced by Newman to get a handle on how the shock wave propagates into the materials. Shock waves can form in gases, they can form in liquids as well as in solids. And unlike acoustic waves, shock waves are nonlinear waves. They do not satisfy the linear equation that I mentioned. So the linear equations, the advantage is if there are more than one wave traveling, you can superpose and generate the state, which is a superposition of these two things. But a shock wave, because it's a nonlinear wave, its velocity, its wave velocity depends on the amplitude. It is not independent of it. And so therefore, you cannot use the principle of superposition, of linear superposition of waves when you're dealing with the shocks. So it obviously goes beyond the linear wave equation. Coming back to where we started from, that we have infinite y and z direction, we launch impact on x direction, and as this propagates down, this particular thing gets compressed uniaxially in terms of strain, but in terms of the stresses, it has three stresses. So in infinite planar impact at the surface leads to a compression wave that it compresses the material in this direction, resulting in a uniaxial strain. We know that in reality, there is nothing like infinite y and z direction. So how does one interpret experiments in terms of the one-dimensional shockwave understanding? Is that you keep these dimensions y and z large enough, and the measurements are restricted in a small region. So by the time the information from the edges reaches the center, that it has been compressed, the material has been impacted, this measurement is over. So the state, therefore, when you're measuring in a small area here or small volume here, that is uniaxial. Now, over a period of time, the information that these are not infinite would reach at the center, and then this compression will no more be uniaxial, will no more represent uniaxial strains. So a few comments in order based on what we talked about. Uniaxial strain emerges due to inertial confinement. We said before, lateral dimensions begin to release. Only during that period, the strain is uniaxial. He stated that truly planar impact leads to compression waves. That would be so in a homogeneous isotropic solid or a fluid. In reality, when there are anisotropic solids, it may be more complicated. It not be a compression wave only in one direction. There is likely to be the shear deformations and so on. So complications arise when you are dealing with materials not close to isotropic or isotropic. Also, impact. See, when you design an experiment, this is okay mathematically to make an assumption that an impact is planar. It just comes and makes an impact only parallel to the YZ direction. In reality, it doesn't happen. Any object, any projectile that you may design, when it comes flying, it may have a slight tilt, and therefore it may, depending on the tilt of the projectile that is coming and hitting, it may alter the results. So therefore, shockwave experiments require that the tilt be kept very low. And in most of these experiments, the tilt is measured to rule out that some of the results seen are not artifacts of inclined impact or having a significant tilt in the impact. And impact would lead to large amplitude stress waves. And as I said, whether it be a shock wave or not, it requires it to be supersonic. And we will see as we go along that it has to satisfy certain conditions before a wave becomes shock. This we discussed earlier that when atoms are brought closer to each other, this is how the interatomic potential changes. In the beginning, these attractive interactions till it reaches the equilibrium value. And as you compress a material beyond its equilibrium value, the repulsive forces take over. Material has to be compressed against this repulsion. In terms of the PV plane, what we notice is as you reduce the volume of a material, at higher and higher stresses, this compression curve changes shape. It's not linear, it is a non-linear curve. So a large compression wave like shock wave or large amplitude wave, therefore, would not have same amount of speed as material is subjected to this. We noted, as I said, material become less compressible as they are compressed to higher and higher pressures. This increased stiffness would lead to increased sound speed. So that means as you compress the material more and more, as derivative of the pressure with the density increases, the sound speed increases. And therefore, the material would have a lot higher, a wave would have a lot higher speed than it represents a higher compression. Let's see how actually the wave shock wave takes shape. The view here, let us view that we are seeing a wave go past as a function of time at a particular value x. So we start from 0 at slowly builds an amplitude, and then it falls back 0 again. If the pressure is not large, then there may not be much modification as the time passes. It may stay as it is because it falls in the category of linear waves. So the low amplitude, such as low amplitude sound waves, they may not change shape or much shape as we go along. But if it's a large amplitude wave, see what is going to happen. So as it propagates at time t is equal to t1, this is the kind of a shape it had. And depending on its pressure value, different part of the wave will move with the different velocity. The foot will move almost with the sound velocity, and this will move with larger than the sound velocity, and this will move larger than this, and so on. So as this wave propagates, you will see this moving, this hump moving forward, and eventually steepening up. This can't move as fast as this, so this catches up. So you will have a shock wave forming at this track. So the velocity of this is a sum of the sound speed and the particle speed. We will see what we will discuss in some detail about the separation of these two concepts, about what we call as the wave speed and the particle speed. Basically, at this time, it is important to recognize that because it's a high compression wave or large amplitude wave, the foot of the wave, if it is not already shock, moves slower than the top, and eventually it shocks up to form a steep edge, giving rise to or representing a discontinuous jump in the thermodynamic variables. And also the speed of this, as mentioned, is a sum of amplitude speed, or let's say the value of the sound wave at that particular amplitude, and particle velocity. So the shock wave velocity is higher than the sound speed in the undisturbed material. So one defines the shock as a wave which is supersonic with respect to the material ahead. That's an operational definition. Basically, a shock wave is kept steady by balancing of non-linearities. The non-linearities which sharpen the front, as we argued, that different part of the wave move with a different speed till we sharpen. And at the other end are diffusion interactions. We said that the sharpness cannot be allowed to become infinite. So thermal conduction across the interface, or generation of defects, or effectively what does this viscous drag or the viscous forces, or the other end. So there's a competition of these two, and that is one keeps a shock wave as a steady wave so long as they balance each other. See, in contrast to what an example that we gave in the previous slide, into which you said a kind of a wave, large amplitude wave as it progresses in the material will shock up. See a situation here is represented. Here was the initial state, it shocked up. And then, of course, as I mentioned, at some stage it will get unloading. Unloading has the other exactly opposite set of situations. This is moving faster, this is moving slower because this is zero amplitude. So as it moves further, this is going to be spread out. It's going to be spread out. There is represented. Part is going to move faster, this is going to move less faster, and this is the slowest. So as we go along, this gets spread out. So in a compression wave, the particles are accelerated in the direction of propagation. In the unloading wave, they are accelerated in the direction opposite to the propagation. So the shock wave, so the unloading wave becomes less and less steep as it progresses. So I guess we will stop here today. If you have any questions, I'll be happy to answer those. We will go in describing mathematical conditions which connect the unshocked and the shock stage in the next lecture, and see the consequences of those to represent the shock state in a material. Thank you. I'll wait for any questions in case anybody has.
No question on WebEx.
If there are no questions, we can as well stop it. And next lecture will be on Friday, same time. All right?
Okay, all right.
All right. Thank you very much. But I can't see, somehow I can't see what happened to the web. You can probably see me.